The current media generation landscape is built on a house of cards. Most developers today rely on sequential pipelines, text-to-speech generators followed by separate lip-sync models, and then disconnected video diffusion frames. This serial architecture creates a fatal semantic gap where information is lost at every transition. In high-budget 2025 AI media campaigns, we have seen massive failures where a character's subtle emotional inflection in the voice simply did not match the micro-expressions of the video. This happens because the audio and visual elements are generated in disconnected latent spaces, leading to the dreaded uncanny valley effect and astronomical post-production costs. This failure isn't just a minor bug, it is a structural limitation of the multi-step approach that causes massive error propagation and latency. This lecture will expose the architectural flaws you've been ignoring and provide the blueprint for the unified future of AI media by the end of this session. To stay competitive in the 2026 market, we must move beyond stitching and embrace joint generation. Unified generation means processing text, image, and audio within a single transformer block or a shared joint latent space simultaneously. Unlike the legacy pipeline where errors accumulate at each stage, unified models like the ones we'll discuss today ensure temporal and semantic consistency across all modalities from the very first token. Think of the transition from a relay race where the baton is frequently dropped to a synchronized swimming performance where every movement is inherently linked by a central nervous system. This architectural shift is what separates a primitive AI wrapper from a next-generation media engine capable of true realism. This is no longer an optional luxury. It is the new standard for enterprise-grade generative infrastructure and IT strategy. But wait, is this unified approach truly more efficient, or does it introduce even greater computational complexity? The answer lies in the fundamental paradigm shift we will explore in the next chapter, titled The Paradigm Shift to Unified Multimodality. The sequential pipeline we've relied on for years is a house of cards. In traditional workflows, we generate text, send it to a TTS engine, then use that audio to drive a lip-sync model, and finally composite it into a video. This approach suffers from massive latency and cumulative error propagation. Each step acts as a bottleneck, where a 10% artifact in the first model grows into a 50% failure by the final rendering stage. From an information management perspective, this represents a high-overhead architecture with excessive data movement between isolated silos. Engineers spend more time building glue code than innovating on the core logic. This fragmentation leads to a significant integration tax that enterprises can no longer afford to pay in the fast-paced 2026 market. Question: does adding more layers of post-processing really solve the quality issue, or are we just masking a fundamental architectural flaw? In 2026, the paradigm has shifted to native multimodality via the single-pass engine. Unlike separate models, a unified engine operates on a joint latent space where text, audio, and visual tokens are processed simultaneously in one forward pass. This is not just gluing models together, it is a fundamental architectural unification where the model sees the character's movement while it decides the tone of the voice. This synchronicity is innate, meaning the lip sync is perfect by design because the audio and video frames are generated from the same underlying representation. This mirrors the human brain's ability to process sensory inputs in parallel rather than serial. We are seeing the rise of transformer-based unified decoders that treat all modalities as a single sequence of interconnected data points. Teaser: this architectural shift isn't just about speed, it changes the very math of how content is synchronized, which we will analyze next. The move to unified architectures is driven by hard data on resource efficiency. When we evaluate the total cost of ownership or TCO for media production, unified models consistently demonstrate a 70% reduction in total production time. By sharing model weights across different modalities, we also see a drastic reduction in the VRAM footprint compared to running 4 or 5 specialized models concurrently. In high-volume enterprise environments, this efficiency translates directly into scalability. Instead of waiting minutes for a composite render, 2026 unified engines provide near real-time feedback cycles. This aligns with international standards for AI efficiency and sustainability, where reducing the compute per token ratio is a primary goal for the next generation of IT infrastructure. Payoff: these numbers explain why top-tier media labs are ditching their modular pipelines this year for more streamlined, monolithic cores. Tracing the evolution of generative AI brings us to the multimodal singularity of 2020-26. If 2022 was the year of the text to LLM and 2024 was the breakthrough for high-fidelity video, then 2026 is defined by the absolute disappearance of the boundaries between them. Market adoption has moved beyond early-stage experimentation into full-scale enterprise content engines. Companies are no longer asking how to make a video, but how to generate an entire brand experience where the copy, the voice, and the cinematic visuals are all conceptually aligned through a single prompt. This shift represents a massive change in content scaling strategy, where the marginal cost of creating multisensory content has plummeted. Question: is this the peak of efficiency, or are we missing one critical component in how these complex engines are classified? To conclude this chapter, the fundamental difference between the old way and the new way is the shift from integration to innate capability. In the past, we acted as system integrators, manually stitching together disparate AI models. Today, as media architects, we leverage single-pass engines that possess zero-latency coherence. This means the semantic meaning of the text is physically woven into the frequency of the audio and the motion of the pixels. This architectural leap provides a competitive advantage in both production speed and creative consistency. For any professional in the media technology space, understanding this transition from multimodal pipelines to unified monolithic cores is non-negotiable. Now that we understand the why of the paradigm shift, we must look at the how. In the next chapter, we'll dive into the systematic classification of these unified engines and how to select the right architecture for your specific needs. To architect a truly unified multimodal system, we must first categorize how different data streams interact within the model's core. In traditional AI, we often spoke of early fusion where raw data is concatenated, or late fusion where separate model outputs are merged. However, the 2026 unified engine paradigm revolves around joint fusion. Here, text, image, and audio are mapped into a shared representative space from the very first layer. This approach, often seen in the latest Omni architectures, allows the model to understand the semantic relationship between a spoken bang and the visual flash of an explosion simultaneously. From a professional engineer's perspective, this reduces the cumulative error typically found in multi-stage pipelines. By treating every modality as a sequence of tokens in a single transformer backbone, we achieve a level of coherence that was previously impossible. But does this mean every data type is treated exactly the same? Not quite. Teaser: the way these models actually generate these tokens varies significantly between two dominant philosophies, which we will compare next. In the current landscape, two titans dominate the unified generation engine: autoregressive transformers and multimodal diffusion models. Autoregressive models, following the lineage of GPT-4 and its successors, treat everything as a next token prediction problem. This makes them exceptionally strong at reasoning and maintaining logical flow across text and voice. On the other hand, unified diffusion models excel at high-fidelity visual synthesis by iteratively denoising a shared latent representation. While diffusion provides superior texture and detail in video, autoregressive models are significantly faster for real-time interactive applications due to their single-pass nature. In high-end media production, we are seeing a convergence where autoregressive models handle the structural logic of a scene while diffusion decoders handle the perceptual final pass. Choosing between them isn't about which is better, but which fits your latency and quality requirements. Question: but how do these abstract methods translate into a concrete system architecture that an engineer can build? Let's look at the actual technology stack. A production-ready unified multimodal engine is more than just a model. It is a sophisticated technology stack. At the bottom, we have the universal tokenization layer, which converts raw pixels, audio waves, and text into a unified numerical format. Above this lies the joint embedding space, where the model understands that the word ocean and the sound of waves are semantically identical. The core reasoning engine, usually a massive transformer, processes these tokens in a single pass. Finally, the multi-head decoding layer branches out to generate the specific outputs requested. This layered approach allows for single-pass generation, where a video is created with its corresponding soundtrack and subtitles perfectly aligned from the moment of inception. This architecture minimizes the uncanny valley effect in AI media by ensuring every modality is rooted in the same logical context. Now that we understand the how, we must address the how. Well, how do we actually measure the success of such a complex system? Evaluating a unified multimodal output requires a paradigm shift from traditional single-mode metrics. We can no longer rely solely on BLU scores for text or FAD for images. In 2026, the gold standard is cross-modal alignment accuracy. This measures how well the visual events in a video correspond to the timing of the audio and the descriptive accuracy of the text. We also track temporal consistency to ensure that a character's appearance doesn't drift across frames, and perceptual quality to gauge human-like realism. Professional frameworks now utilize automated evaluator models, specialized AIs that watch and listen to generated content to score its logic and sync. For instance, if a generated video shows a glass breaking but the sound occurs 200 ms late, the sync accuracy score drops. These KPIs are essential for moving from experimental prototypes to enterprise-grade media solutions. Micro hook: but how does a lead engineer decide which framework to actually deploy in a production environment? Selecting a unified multimodal framework is a high-stakes decision for any technology leader. It's not just about the flashy demo, it's about architectural robustness. As a professional engineer, I look for 4 critical factors. First, modality scalability: can this engine handle new sensors or data types in the future? Second, inference efficiency: can it generate a 30-second unified clip in under 10 seconds? Third, data governance: how does the model handle proprietary training data and copyright? And finally, deterministic control: can we force the model to follow a specific script without hallucinating visual artifacts? If a framework misses even one of these marks, it will fail in a corporate setting. This checklist ensures that your investment in unified AI isn't just following a trend, but building a foundation for the next decade of media. Bridge: we've classified the engines and defined the metrics. But to truly master this, we must go deeper. In the next chapter, we will explore the shared latent space, the mathematical black box, where the magic of cross-modal translation actually happens. In the legacy era of AI, we treated text, audio, and pixels as separate silos, attempting to bridge them with fragile adapters. By 2026, the paradigm has shifted entirely to the shared latent space. Imagine a high-dimensional mathematical manifold where a specific frequency of a breaking glass sound and the visual pixel patterns of shattered transparency occupy the exact same vector neighborhood. This isn't just matching tags. It is semantic mapping at a fundamental level. For a professional architect, this means the model doesn't learn to sync them, it perceives them as the same event described in different languages. We utilize unified encoders where the semantic distance between a textual description and its visual audio manifestation is minimized to near zero. This fundamental shift eliminates the uncanny valley of timing errors that plagued earlier multi-step pipelines. But how do these disparate signals actually communicate during the generation process? The secret lies in the attention mechanism that binds them together in real time. To achieve temporal synchronization between a flickering flame and its crackling sound, we employ cross-modal attention. In this 2026 architecture, the query key and value matrices are no longer restricted to a single data type. When the video stream generates a frame of an explosion, the query from that visual frame searches the latent space for corresponding audio keys. This ensures that the boom isn't just triggered, it is architecturally bound to the peak of the visual light intensity. This is what we call causal binding. Unlike the 2023 style stacking of models, this single-pass attention mechanism processes all modalities in parallel within the same transformer block. This prevents the cumulative error common in pipelines where a delay in text processing would eventually lead to a drift in video-audio alignment. However, keeping this complex system stable during training is a massive engineering challenge. To understand the stability, we must look at the specific loss functions that govern this mathematical harmony. The glue that holds this shared space together is the contrastive loss function, specifically optimized for multimodal density. In a production-grade 2026 model, we utilize variations of inference loss to maximize the agreement between true pairs like a lion's roar sound and a lion's open mouth image while pushing away mismatched pairs. Look at this pseudocode logic. We aren't just training a classifier, we are training a world simulator that understands the statistical co-occurrence of physics. By minimizing the distance between the visual latent and the audio latent in our loss function, the model learns that the texture of metal should produce a specific metallic resonance when struck. This joint optimization is why modern models can generate a video of a rainy street where the sound of every individual droplet matches the ripple seen on the screen. It is the pinnacle of generative architecture, moving from guessing to simulating reality. But does this mimicry actually resemble how our own brains process the world? The answer leads us into the fascinating intersection of AI and biological mimicry. Single-pass synthesis represents a monumental shift from assembly line logic to biological growth. In a standard pipeline, you build the skeleton text, then the skin image, then the movement video, then the voice. But in unified generation, the model exhibits emergent behavior where the modalities develop simultaneously, much like how the human brain processes sensory inputs via the thalamus. When you think of an apple, your brain doesn't fetch a picture and then wait for a crunch sound. The concept is holistic. In 2026, our unified models achieve this by treating the generation as a single diffusion process across a concatenated latent vector. This cogeneration ensures that the physical properties of the generated objects are consistent across all senses. If the AI generates a heavy stone falling, the impact sound is automatically deep and resonant because the heaviness is a property of the latent concept, not a post-processed effect. This is the ultimate goal of the information management professional, creating systems that don't just look right, but behave right. But don't be fooled, this biological mimicry comes with a heavy price in terms of hardware. Let's address the hard reality, the infrastructure required for this shared latent space. Many engineers ask if their current H100 clusters can handle single-pass unified models. The truth is, VRAM is the primary bottleneck. A unified model with 100B parameters, handling 4K video tokens and high-fidelity audio tokens simultaneously, requires massive memory bandwidth. In 2026, we solved this through mixture of experts, MOE, and 4-bit KV caching, allowing these giants to run on enterprise-grade edge servers. Another common question is about latency. While a single pass might seem slower initially, it eliminates the cumulative latency of passing data between 5 different models in a pipeline. In a real-world enterprise scenario, the single-pass architecture actually reduces time to first frame by up to 40%. This is the trade-off you must manage: higher upfront hardware costs versus significantly lower operational latency and superior output quality. Understanding these constraints is the difference between a theorist and a true IT strategist. Now that we understand the deep mechanics, the question is, how do we actually deploy this in a business environment? In the next chapter, we will bridge the gap between this theory and real-world enterprise strategy. By 2026, the traditional pipeline of chaining individual models for text, image, and voice is no longer viable for enterprise-grade responsiveness. In a modern microservices architecture, the unified multimodal model acts as a singular intelligence core rather than a series of disparate API calls. This shift reduces the tax of integration, the latency, error propagation inherent in multi-step processing. When deploying these architectures, architects must focus on the unified inference layer, which handles the joint distribution of multiple tokens in a single pass. This ensures that a digital human's facial expression, vocal tone, and verbal content are perfectly synchronized by design, not by post-processing. However, integrating this into legacy systems requires a specialized AGI gateway capable of handling massive throughput and stateful multimodal streams. Question: this centralized approach seems efficient, but how does it actually change the way we build interactive user experiences? In the real world, the most profound impact is seen in conversational fluidity. Previous systems required the AI to finish thinking in text before it could start speaking or moving. In 2026 gaming and high-end customer service, we use unified models to enable interruptible AI. Because the voice, text, and animation are generated in a single pass, the AI can react to a user's interruption in under 200 milliseconds. Consider a medical simulation or an immersive RPG where every subtle micro-expression and vocal inflection must match the medical urgency or the narrative tension instantly. This level of synchronization is impossible with sequential models due to the cumulative latency of the ASRILM-TTS lip-sync chain. However, this power comes with a significant trade-off in complexity and monitoring. Payoff. Until now, we focused on the speed of creation, but in the next segment, we will reveal the hidden risks of letting a single model control every sensory output. Deploying a unified model is not without its perils. We face a new phenomenon called cross-modal hallucination. This is where the text generated might be factually correct, but the accompanying audio tone or facial expression conveys a completely different, perhaps inappropriate, emotion. From an information management perspective, this creates a massive challenge for AI governance and compliance, specifically regarding ISO 42001 standards. If a single black box produces all modalities, debugging which part of the latent space caused a biased output becomes significantly more difficult than in modular systems. Enterprises must implement multimodal guardrails that monitor not just the text, but the sentiment of the voice and the safety of the generated imagery simultaneously. Teaser: if the risks are this complex, how do we prepare for the next generation of models that go beyond just sight and sound? As we look toward the horizon beyond 2026, the trajectory of scaling laws suggests that unified generation will expand to include haptics, spatial data, and even biochemical signals. We are moving from content generation to world simulation. In this future, the AI doesn't just show you a video, it generates a consistent 4D environment where every sense is synchronized through a unified latent representation. For architects, the strategy must be future-proofing through modality agnosticism. This means building systems that don't care if the token is a word, a pixel, or a vibration. By mastering the single-pass unified architecture today, you are preparing for the era of total sensory immersion. Bridge: we have covered the principles, the architecture, and the strategy. Now, it is time to synthesize everything into a final blueprint for the future in our concluding chapter, the architect's conclusion. As we conclude this exploration, the most critical takeaway for an IT architect is the shift from modular pipelines to unified latent spaces. By 2026, the traditional method of chaining specialized models using a text-to-image model followed by a video-to-video model will be viewed as a legacy approach fraught with high latency and semantic drift. In a single-pass architecture, we leverage a shared embedding space where text, image, and audio tokens coexist. This joint modality convergence ensures that every frame of video and every wave of audio is perfectly aligned with the original semantic intent, drastically reducing the hallucinations that occur during model-to-model handoffs. For enterprise-grade systems, the focus must shift toward optimizing high-bandwidth inference engines that can handle these unified multi-token streams. We are no longer just managing data. We are managing the orchestration of a singular generative pulse. This transition represents a fundamental leap in efficiency and creative fidelity that defines the next generation of media services. But wait, if every pixel and decibel is born from the same mathematical seed, what happens to our traditional concept of originality in media? The year 2026 marks the era where the boundary between synthetic and real media dissolves into a singular reality vector. We are moving toward reality as a service, where the generation process is not about assembling parts, but about sampling from a multidimensional latent representation of the world. In this new paradigm, originality is no longer defined by the medium of capture, but by the precision of the architect's prompt and the integrity of the underlying model weights. As information management professionals, our responsibility evolves from simply storing assets to governing these generative engines and ensuring ethical alignment across all simultaneous outputs. The obsolescence of the multi-step pipeline isn't just a technical update, it's the birth of AI-native media that is born fully formed across all senses. This requires a new mindset, one that prioritizes systemic coherence over individual tool proficiency. Are you prepared to architect a system where the input is a single strategic thought and the output is a perfectly synchronized, multi-sensory universe? This concludes our journey into the future of unified AI, but the real architectural challenge begins the moment you start implementing these principles in your next-generation infrastructure.